is cast iron pipe of internal diameter 1000 mm and 50 mm thick, carries oil. The pipe is supported at 2 points 10 meter apart. Find the maximum stress in the pipe. Take weight of cast iron as 72 kilonewton per meter cube and that of oil as 9 kilonewton per meter cube. It's actually weight density of cast iron and oil is given. Okay. Now let us try to solve this numerical. What I will do is first we'll just try to draw the cross section of the pipe for our reference. So this is the internal diameter of the pipe, and then this is the outer diameter of the pipe. Now he says that this diameter, that is your internal diameter, is 1 meter or 1000 mm. Okay, and this thickness is 50 mm. Let me just write down that. So this is 1000 mm and this is 50 mm. Okay, this is the cross section and the oil is inside here. Right. Now he has also mentioned that the pipe is supported at 2 points which is 10 meter apart. So I can assume it as a simply supported beam like this, right? And I will be having two supports like this, and on the entire length of this pipe uh, there will be load due to the pipe self weight and the oil present in this. So I will just show this as rectangle. I am drawing the cross section. Okay, and let me just shade this inside. Okay, so this is my arrangement that is given in the numerical, and the distance between these supports is given as 10 meters, right? So this is 10 meters. Okay, so what we have to do is first we have to find the load on the beam and then we have to start. So let me start with this. Okay, now see I have two weights here. One is of the cast iron pipe and the other is the oil which is present inside this. right? So weight per meter length of pipe with oil, right? This is equal to, now uh, weight is calculated by volume of the particular cross section into the weight density, right? So volume into weight density of CI pipe plus volume into weight density of oil, correct? Now what is the volume of the pipe? Volume of the pipe is uh, 5 by 4 into the outer diameter, that is d square, minus inner diameter, I'll call that as d square. 5 by 4 d square minus d square into length plus volume of sorry, into WCI. I'll write it like this. So this is weight density of cast iron. Then I have volume of the oil, that will be 5 by 4 into d square, because it is only inside the pipe I have the oil, into L into W oil. Now let us substitute the values. Before that, let me calculate D and D, right? So now see, this weight is given in kilonewton per meter cube. So better we substitute the diameters in meter, right? So now D is equal to internal diameter, which is 1000 mm, which is 1 meter, right? And capital D is the outer diameter, this diameter, which is 1000 plus 50 on this side and plus 50 on the other side. So 1000 plus 2 into 50, which is equal to 1100 mm, which is equal to 1.1 meter. And L is equal to 1 meter, because I have written weight per meter length of pipe with oil, right? So L here I am taking as 1 meter, or I'll make this as, let it be like this. Okay. Now let us again calculate this. Oil is equal to, first 5 by 4 remains as it is, into t square is 1.1 square minus d square is 1 square into 1, you can make like that, into weight density of cast iron is 72 kilonewton per meter cube. So this is in meter cube now, meter square, right? Into L is 1. I'll just put that also here. So this meter square into meter, so this becomes meter cube, and meter cube gets cancelled. So this you will get it in kilonewton per meter length. This plus, I'll just copy this as it is and modify 5 by 4 into d square into 1 into this is 9 kilonewton per meter. So the unit will be kilonewton per meter. Now let me just calculate this. 5 by 4 into 1.1 square minus 1 square into 72 is this plus 5 into 1 square is 1, 1 is also 1 into 9 by 4. So it is 18.944 kilonewton per meter. So I can consider this to be a uniformly distributed load on the beam, right? So for a uniformly distributed load, the maximum bending moment is at the center of the beam, which is simply supported, and the maximum bending moment is given by, anybody remembers? Maximum Bm is at middle of the span and is given by Bm max is equal to WL square by 8. We had done this derivation where W is the uniformly distributed load intensity, right? So here this W is 18.944 kilonewton. So we have to just substitute 18.944 here, and L is the total length or the span of the beam, right? So this is equal to W is 18.944 kilonewton per meter into L is 10 square of it by 8. So this is 18.944 into 10 square by 8. So 236.8 unit is kilonewton meter bending moment, right? Kilonewton meter. If you do not remember this formula, we can do the usual way we used to in unit number 2. Find the support reactions and then at the midpoint find the bending. You can do it that way also. You will get the same answer, right? So this is the maximum bending moment which is occurring at the mid of this pipe. Now I can find the bending stress. Now in order to find the bending stress, I need to first find the moment of inertia of the pipe. Now remember one thing, see the oil contributed to the weight, but it does not take any stress. Oil flows through the pipe, cast iron pipe. It is only adding, increasing the bending moment. It is not going to take any load. So the moment of inertia we have to calculate is only of the pipe, this annular region that is there. You have to calculate the moment of inertia of that pipe only. Okay, so please don't take it as a complete circle. It's not a solid uh, shaft, right? Now, moment of inertia of pipe is equal to pi by 64. It's a hollow circular cross section. For circular cross section, it is pi d power 4 by 64. Now, for hollow, it is pi by 64 into d outer diameter d raised to 4 minus inner diameter d raised to 4, right? So this will give you the moment of inertia of this pipe. Now let us substitute the values in this. Pi by 64 into d is 1.1 raised to 4 minus b is 1 raised to 4. So this will be, or I'll put it in millimeter because I will get the answer directly in, or this is also in kilonewton meter, so I can keep it in meters also. That is not a problem, right? So 1.4 raised to 4. 1 raised to 4 will be 1 only, minus 1 is this into 5 by 64.
Hello, sir.
Yes,
Sir, it should be 1.1 na.
yeah, it is 1.1.
You check in 1.4, sir.
Oh, sorry. Okay, I entered 1.4 in the this thing, is it? Okay, I'll correct it again. I'll do. I is equal to 5 by 64. I'll directly put the values now. 1.1 raised to 4 minus 1 raised to 4. 1.1 raised to 4 minus 1 is this into 5 by 64, right? And is there anything in this? Let me just copy this. Um, 3, 6. I put a point here and plug it this 6. Okay, this into 10 raised to minus 6 meter raised to 4. This is not mm, this is meter raised to 4. So be careful with the units. If you're getting confused with the units, keep everything in millimeter. That is very safe, right? So you can change bending moment also in Newton mm, and then you can solve this. That is also, you will get the same answer, right? Now, since it is a circular cross section, it is symmetric, right, about both the sides above and below the neutral axis. So max bending stress is at outer surface of pipe where y is equal to d by 2, right? Now let us find this. Bending stress is equal to formula is my by I, right? Now m is 236.8, right? So this is in kilonewton meter, right? So if you substitute as it is, the answer you get will be kilo newton per meter square, right? So that will be kilopascal. So I try to get the answer in pascals. So what I will do is I will multiply this by 10 raised to 3. So this is Newton meter now, right? M is in Newton meter into Y is B by 2, D is 1.1 by 2 by I is 2778.1.46 into 10 raised to minus 6, right? Now,
बनवता तर आलं पाहिजे ती तेवढा सुटते का फक्त भात भाजी करत आणि तुझ्या प्रवाचा होता
yeah, what is this? Sahil, please mute your mobile.
नव्हतं देतो बनवून खा बाबा हा खायची काही सांगत मी आपलं काम
Sahil, please meet me after the lecture. Call me. Okay, so let us calculate this bending stress. 236.8 into sorry 236.8 into basically 1000, right, into 1.1 by 2 by 27781.46 into by uh, minus 6 ये कुछ और ही हो रहा है just calculating my calculator. It is 236.8 kilo into 1.1 by 2 divided by 27781.46 exponential minus 6.
So 10, it's 10 to power minus 6 now.
Yes. How much you getting? But a huge value. This is equal to 4688018, right? 0.6 Newton per meter square, right? Now, 1 Newton per meter square is 1 Pascal, right? So, if I take here, then it will be 4.6 0.688 megapascal or Newton per mm square. If you use millimeter in the calculation, you will be getting 4.688 Newton per mm square. I used meter, so I got 4688018.6 Newton per meter square, right? And 10 raised to 6 Newton per meter square or Pascal is equal to 1 megapascal, and 1 megapascal is equal to 1 Newton per millimeter square, right? So this is the maximum stress that is induced in the